class of Electrodynamics 1. Dear students, in the last lecture we discussed about the spherical coordinates. What are the spherical coordinates? How do we can represent a vector in spherical coordinates? What are the different directions of spherical coordinates? In this lecture we will discuss infinitesimal displacement in spherical coordinates, infinitesimal volume in spherical coordinates, infinitesimal area in spherical coordinates. These infinitesimal elements are very important because these infinitesimal elements are used to find out the different types of the integrals, such as the line integrals, surface integrals, volume integrals. In the first we discuss the infinitesimal displacement. What is the infinitesimal displacement? Infinitesimal displacement actually is the small displacement in space. Small displacement in space if the small displacement in space is along the direction of r, displacement is in the direction of
dl is, which is the infinitesimal displacement. dl is infinitesimal displacement. This would be equal to simply dr into r cap, because its direction is along the increasing direction of r. If you have a coordinate system x, y, z, remember that if a point P is represented by a spherical coordinate, then this length is represented with the r, and its increasing direction is the direction of r, which is denoted with the r cap. If you move along this direction from here to here, this direction is this infinitesimal displacement is dr. So if you move from here to here, you cover a small displacement along the direction of r, then this infinitesimal displacement will be equal to dr into r cap. And if the small displacement is along the direction of theta, in that case dl would be equal to not d theta only, because d theta is the angle and infinitesimal displacement is the length. In that case dl is not equal to d theta, but it is equal to r d theta. How? I explain it here. If you have a coordinate system x, y, Z, and suppose this is the field point, and this radial line makes an angle theta with the Z axis. If you cover infinitesimal displacement along the increasing direction of theta, increasing direction of theta, this direction would be if this line move, a radial line move in a vertical plane. So if this radial line moves slightly, suppose this radial line move angle d theta, in that case what would be the infinitesimal displacement? This angle is the d theta, then infinitesimal displacement, which is the length, we can find out this length, which is this would be equal to using the formula of S is equal to r theta, we can find out r d theta if this is the ds. In this case this would be ds, this is equal to r, which is the radius, and so infinitesimal displacement would be equal to r d theta. If the small displacement is along the direction of phi, dl will be equal to not d phi, but dl would be equal to r sine theta d phi. How? Here I have not represented the direction of the dl. The direction of dl will be along the theta cap. In this case, if you draw a Cartesian coordinate system, this is the radial line, and you draw a projection from here to here. If the radial line rotates to some other angle, then you get the two different points. It means phi is changed, which is the d phi. What is the length of this line? Remember spherical coordinates. Length of this line is equal to r sine theta. R sine theta, because these two lines are parallel, this line and this line, these two lines are parallel, so this line also has the length r sine theta. So what will be infinitesimal displacement due to change of phi coordinate? This will be length of this arc represented by this green line, and length of this arc will be equal to using the formula of S is equal to r theta. In this case r is equal to r sine theta and angle is the d phi, so infinitesimal displacement will be equal to r sine theta d phi. So due to change of phi, the infinitesimal length dl will be equal to r sin theta d phi, and its direction is along phi cap. So this is the case when infinitesimal displacement is along some particle coordinate. If infinitesimal displacement is in space, in that case the change of r, change of theta and change of phi occurs. In that case infinitesimal displacement will depend upon are these coordinates, and so if the infinitesimal displacement is in space, in that case we can write the infinitesimal displacement. Displacement is in space then dl will be equal to some infinitesimal displacement due to change of r into r cap plus infinitesimal displacement due to change of theta into theta cap plus infinitesimal displacement due to change of phi into phi cap. Infinitesimal displacement due to change of phi is represented by dl phi, and due to theta is represented by dl theta, and due to r is represented by dl r. So putting the values of dl r, this is the dlr, value of dlr, this is the value of dl theta, this is the value of dl phi. Putting here we get the infinitesimal displacement in space. dlr is equal to dr into r cap plus dl theta is equal to r d theta into theta cap, and dl phi is equal to r sin theta d phi into phi cap. So this is the value of infinitesimal displacement in space. Now what is the infinitesimal volume? Infinitesimal volume is the product of three lengths. These three infinitesimal lengths due to change of r, due to change of theta, due to change of phi. So we can write infinitesimal volume, which is denoted with deta, is the product of dlr, dl theta, dl phi, and dlr is equal to dr dl theta is equal to r d theta, and dl phi is equal to r sin theta d phi, and so you get the infinitesimal volume equal to r square sin theta d theta d phi dr. Here you can see in this figure, this is the infinitesimal volume which is the represented here. This is the radial direction, and in this radial direction, if you increase the r in the direction of r, which is represented by dr, so it makes the one side of the cube. In this direction, theta is changed because this radial line makes an angle theta. If this radial line rotates in vertical plane, then theta will change, and due to change of theta, the infinitesimal displacement is r d theta. And if this radial line rotates in a horizontal plane from here to here, then phi will change, and due to change of phi, the infinitesimal length is r sin theta d phi, and this will be this side of the cube from here to here. Due to change of phi, it makes this side of the cube, and due to change of r, this makes the height of the cube. So to calculate the infinitesimal volume, which is the cubical shape, will be the product of these three lengths, dlr, dl theta, dl phi, and this infinitesimal volume is equal to r square sin theta d theta d phi dr. Now we discuss about the infinitesimal area. Infinitesimal area, which is denoted with the dA. Infinitesimal area has no general formula like the infinitesimal volume. It depends upon the different orientations of the plane. If the orientation of the plane is changed, then infinitesimal area of that plane will also change. So we here find out what is the infinitesimal area for the different orientations of the plane. Suppose if the area is in the xy plane, suppose area is in on the surface of a sphere, then what will be the infinitesimal area? Infinitesimal area is actually the product of two lengths along the direction of r theta, or along the direction of theta phi, or along the direction of phi r. So if the plane lies in r theta plane, in that case the area, infinitesimal area, will be product of these two lengths dlr into dl theta, and phi will be constant. In that case, phi will be the direction, because direction is always perpendicular to the surface area element. This is the case when this infinitesimal area lies in r theta plane. Phi, this area has the direction along phi cap. In other case, if infinitesimal area lies in theta phi plane, in that case infinitesimal area will be a product of dl theta dl phi, and its direction will be along r cap. In this case theta phi are the variable in this plane, are variables, and r is the constant. In other case, if the infinitesimal area lies in phi r plane, in that case the area, infinitesimal area, is the product of dlr into dl phi, and direction of area will be along theta cap. In that case r and phi are the variables, and theta is constant. I will take the example of area on the surface of a sphere, infinitesimal area on the surface of sphere. On the surface of sphere, suppose this is the figure which is here, which represents the area on the surface of sphere. Suppose this is the part of a sphere, which is the quarter sphere, which is represented here, and this area represent this small area, which is the infinitesimal area, represent the area on the surface of sphere. You know, on the surface, on every point of the surface of sphere, r is the constant, because r is the radius of sphere, so r is the constant. And two coordinates will change on the surface of sphere. What are these two coordinates? Because you can see, if this radial line, which is the r radial line, if this line rotate, theta is changed, and change of theta is d theta, and due to this change of theta the length of this area element will be equal to r d theta, and if this line rotate in horizontal plane, and due to rotation of this line phi will change, and due to change of phi the infinitesimal length is r sine theta d phi, and so these two lengths are the two sides of this area, making this area. So this infinitesimal area on the surface of the sphere is the product of these two lengths. Infinitesimal area is the product of these two lengths, mean product of those two lengths which are changing coordinates, which coordinates are changing. So dA is the product of dl theta into dl phi, and one coordinate which is the constant, it is the direction of r. R is constant, it is the direction of area, sorry. The coordinate r is the constant, so direction of area is along r cap, and you know that value of dl theta is equal to r d theta, and value of dl phi is equal to r sine theta d phi, as we have already calculated it, into r cap equal to dA. This is the infinitesimal area r square sine theta d theta d phi into r cap. This is the infinitesimal area on the surface of sphere. Here we take another example. If you take infinitesimal area in horizontal plane, if the plane is the xy plane, then what would be infinitesimal area? In xy plane. I draw Cartesian coordinate system. This is the x-axis, y-axis, z-axis. Suppose the area lies in this plane. This is the area. Here you can see that the two coordinates will change in this plane. What are these two coordinates? One coordinate is r and other coordinate is phi. Suppose you have the small infinitesimal area here, you can see that this has certain radius r and certain value of phi, because its length along phi has certain change in phi. If you take the infinitesimal area here, then you can see that it has the some other value of r. R is changed in this plane, because at this position the area R is different to this position, and you can see the phi is also changed because here the phi is suppose phi 1, and if you take this infinitesimal area, then phi is equal to phi 2. Phi is changed. What is the constant here? Theta is the constant, because this xy plane makes an angle theta with z axis. What is this angle? If you take any radial line here, these radial line will make an angle theta with z axis, and this theta is equal to 90 degree or pi by 2. So theta is the constant. Theta will be the direction of this area, because if you want to rotate this radial line in the vertical plane, then increasing direction of theta will be downward. So direction of this area will be theta cap, and this direction will be downward. So infinitesimal area dA is the product of these two lengths which coordinates change. dLr multiplied by dL phi, and its direction is along theta cap. dLr you know is equal to dr, and dl phi is equal to r sine theta d phi into theta cap, and infinitesimal area it will be equal to r sine theta dr d phi and theta cap. In this case theta is known, which is equal to 90 degree. Putting here theta is equal to 90, so dA is equal to r sine theta sine 90 is equal to 1. It becomes equal to dr d phi into theta cap. This is the infinitesimal volume in xy plane. Okay, so these are different types of infinitesimal elements, and infinitesimal displacement, infinitesimal volume, infinitesimal area. Thank you very much. Meet you soon in the next lecture.